Today, we are going to start discussing transformers, and I hope done with open circuit test and short circuit test for transformer Monday. Because Tuesday, I'm going to have experimental transformer. If you have any question from now, you may ask. So it'll be easy for you to do the experiments. First, what do you know about transformer? I'm sure that everybody once in his life dealt with the transformer. That's up, step down, step down. That's right. Like when I was traveling this summer, I got to get with me some stuff was 220. I have some stuff 110, and I can get to replace it. So I got to have transformer. Appliances and equipment that the operated both 110 and 220. But when you start to deal with big power, like power transformers, you cannot find something to replace. For example, when we have the laptop, you can plug it anywhere to work. Most transformer and the adapter. But nowadays, using power electronics, you can avoid using transformer. That's why the charger of laptop these days not heavy like before. My days I got heavy one to charge because it has transformer. But now we can do something else using power electronics. But in some application where it's really have to use transformer. You know why? I can if I show you some kind of power transformer, like this kind power transformer, the big one, they call it distribution transformer, that they feed power to houses, to industry. They have big insulator, and even that single phase, three phase is huge. So I'm talking about three phase, even they use it. They don't replace it by something electronics like what we're doing in our laptop. You know why? Why do you think? Why they can do that? They do that with the laptop. But they still need transformer, especially. Question is why these, especially when they are dealing with big power, however, avoid it with laptops, with some appliances. They avoid now using transformer. Even minute chargers, they don't use transformer. I do by myself because I like to do it without transformer. Yeah. But big. Possible. It's not impossible. Yeah.
Is it because of the AC? That's why you need the transformer?
That's AC, and also have power electronics AC. Thyristor track, AC. Power electronics is not cheap.
Performance-based?
Performance?
Yeah, is it based on performance? Is there less of a loss?
Well, the power of transistor, yeah.
Because it's an AC power, now the phone or electricity is an DC power.
I mean, Have you done? So there is nothing transformer you cannot do but. That's a transformer that I'm going to explain now. No, let's get two sides here. Let me show you. Yeah, that's transformer. And what is the thing? The other thing will not be affected. And the high voltage and the low voltage you are directly. The only thing connected both the magnetic field. But in power electronics, the electric currents go everywhere, the low and the high both sides. So that's the reason. So that's very important. That's why sometimes when I was working with electronics, I love electronics. Let's form like that. These are small transistors, not three-phase, not single-phase. And I use it in electronic circuits. The control circuit from the circuit that, because yeah, the huge power transistor can affect us. If there is a fault in a high voltage side, hurting me, it's hurting the electronic circuit itself. We're working with milliampere, so if there is a fault on one side, so it will be affect the other side. So they make isolation transformer. And there are many transformers used even in electronics, like RF, carried about RF transformer, audio transformer, they use it for this application. And that's the transformer used in power. That's single phase. You will, when we go three phase, I'm going to show you the three phase. For example, that's distribution surface transformer, the one here to the right, and has center tap. And they have like here, that's the voltage, and they can divide it into two, so they can distribute to different houses. Or inside the house, you can use different lines. That's one for the appliance, very normal transformer, and that's how it's connected. That one exactly like this one, but I'm showing you the insulator because of the high voltage. Use huge insulator. So how transformer work? According to the magnetic circuit that we explained last lectures, you should have two sides, primary and secondary, but we say that if you have a coil in general, and there is a current in this coil, it will produce magnetic field flux phi. And we always express the flux in general by flux or linking flux lambda, which is equal n phi. Always we do that. That's general case. If n is equal 1 turn would be phi, but in general, n phi, this is the flux. And the total flux linking lambda, if it's changing with time, so it produces voltage. So that's the whole idea. So when you go for the circuit here, that's the primary side. You apply voltage V1 alternating with the frequency F, and it will produce current I1. I1 will go through this coil in this direction, and because there is current in the coil, it will produce magnetic flux. And the magnetic flux everywhere. I said when you see in the textbook like that, it does not mean this is the only magnetic field that in the core. No, it's everywhere. But as you know, the field, every time you go farther, it gets weaker. And there are some here that they are not linking with the other side. We don't care about it. It's lost. But the only one that we care about, the flux, which is linking both sides, because this flux will be responsible for producing the electromagnetic force, EMF, the voltage on the other side. So if you have the flux phi produced by I1, it will produce flux phi. And if you have the number of turns issue N2, so you have the flux in the other side, or linking flux is equal N2 times phi. However, the flux linking to the primary side, it's equal N1 phi. And phi is the same for both because it's common. So that's the flux linking. And that will produce the voltage. Let's just see how we calculate it. So you have the current I1 produce flux, and on the other side you will have the flux linking to the coil on the secondary, which is equal N2 phi, as I showed. Phi is function of time, the magnetic field function of time. Why? Because the way that the flux changing with time, it's the same as the current changing with time. Which current? The current that produced this magnetic field. So magnetic field shape, exactly the same shape of the current, except there is, of course, phase shift. So phi in general, function of time, it will be the maximum value of it, sine. Get it? What's omega? Omega is 2 pi f. What's f? It's the frequency. Frequency of what? Frequency of the current. What is the frequency of the current? It's the frequency of the voltage supply, V1. So when it linked the secondary, you got the coil on the secondary side N2, and the flux going to the side phi, and we'll calculate already lambda 2 will be equal N2 times phi, and phi m sine omega t. That's the flux linking the second coil. So it will produce EMF here, E2. E2, what is the relationship between E, the voltage produced by the magnetic field within this relationship? And the flux. Yes.
E is equal to
Equation. The relationship between E and lambda. Lambda is fixed. Are you going to have induced EMF? Battery producing DC. This coil. Do you think that voltage will be produced? Because it has to be some kind of relative motion, right? It has to be changing. So we have a changing flux, as you see. It's function of time. sine omega t. So it's varying. If you can sketch it, that's the phi, and this is the lambda. Both are the same. So yes, we did the relationship. We said that E is equal the rate of change of flux line. You had this in physics. You had N d phi by dt. And I accidentally last lecture, and we removed the negative sign because the negative sign just shows us direction. Now our interest only in the magnitude. So now you can say E2 is equal to the differentiation of the flux linking to the coil. So you have N2 is constant, phi m, the maximum value is constant. Then you differentiate sine omega t. What's the differentiation of sine omega t? Cosine omega t times omega, right? Because you are differentiated with respect to time. So you can say that E2 is equal N2 phi m omega. Let's just make it more detailed. N2 phi maximum and omega is equal to phi f. And here you have the cosine omega t. Let's say that the whole value, that's the maximum value of the voltage. Just call it E2 maximum, all this value. So be E2 cosine omega t. That's the voltage produced or induced in the coil on the secondary side. Has a maximum value and changing with cosine. What do you observe? The flux which induced this voltage, it's sine. Maximum value sine, and E produced its cosine, right? So that's why when you do the relationship, the phasor relationship between both, you'll find that's the EMF and that's the flux. 90 degree between the sine and the cosine. Well, that's the maximum value, and if you sketch, should be cosine, so that's sine. And if we want to sketch on the same graph cosine, would be like that. That's E cosine. The maximum value, we're always interested in maximum value or root mean square when we are dealing with sinusoidal voltage or current. Root mean square, right? Effective value. You can call it effective value or RMS. Well, what's the RMS? How we get it? If you have the maximum value, you divide the maximum by square root of 2. All right. So I'll say that the root mean square for A2 will be equal to E2 maximum value divided by, because the height here, that's E max, divided by root 2. What's E2 max? That's the whole thing. N2 phi m 2 phi f divided by root 2. Observe that you have some constants here. 2 and pi constant, and radical 2 is constant. You can say 2 pi over radical 2. And then you have N2, you have f, you have phi m, right? Yeah. This value, if you do it in the calculator, you find it's a really nice number. I remember that when I was students. Well, like 4.44, all fours. That's good. So 4.44 M2 F phi m. So if you want to calculate the root mean square of the voltage induced by magnetic field, it depends on the maximum value of the magnetic field, the frequency of the supply, the number of terms in N2. Remember, it's induced voltage also on the other side, on the elementary, on the primary side. So I can just say that if you like, I don't have to derive it now. I can say just E1. I'll drop RMS because when I use this one without max, it means root mean square. E1 will be very simple. It will be 4.44 N1 F phi m, because phi m is linking both coils, right? And while the root mean square of the induced EMF on the secondary side, E2 is equal 4.44 into F phi M. So what is the relationship between E2 and E1? The same, if the same, just the terms, right? So that will be the ratio between the induced voltage on the secondary side, the induced voltage on the primary side, N2 over N1. That's the terms ratio. So if you have a transformer, that's N1 and that's N2. The produced or induced voltage E1, E2. So the ratio between the voltage induced in both coils is equal to the ratio between turns ratio, between the turns ratio. Yeah. So if you want to have a step up, you make N2 greater than N1. Well, it depends on the definition of turns ratio. So if you have we call it turns ratio, I will choose N1 by N2. Some textbook use N2 by N1. Doesn't matter. You can do that. So in this case, you need N2 greater than N1 for step up. And you need N2 less than N1 when you have step down. If you have N1 equal N2, so it will be like no step up, no step down. Usually they will use this in isolation purpose only. So that's the theory behind the transformer. How you step up, step down, increase the voltage, decrease the voltage, depends on how you just play with the number of turns. You increase the number of turns on the side where you want to increase the voltage magnitude. What about the current? Because you have in this transformer I1 and you have your I2. Well, there is a theory that we understand and we believe. As I said before, there is nothing. You give system energy or power, you get it out, minus loss. That's, I mean, the general rule in the universe. So let's assume, or let's just forget about the losses now for simplicity. So what is the power input? P1 will be equal E1 I1. What is the power of the output? E2 I2. Assuming ideal transformer. You will have P1 is equal P2. So you have E1 I1 equal E2 I2. That's the relationship between E2 and E1. We said that E2 over E1 is equal N2 over E1, directly proportional to each other. But what about the I2 over I1? I2 over I1 will be equal E1 over E2, right? From this equation for the power balance in the transformer. Input power equal output power. So you have, so the current and the voltage inversely proportional to each other. So I2 over I1 is equal E1 over E2, which is equal to N1 over N2. So always put in your mind that when you find the ratio between the voltage will be the same subscript like E1, you find N1 corresponding to E2, but the current, they are opposite. It comes from the power. And again, life is fair. This is equal to A. That's right. If you define A as N1 over N2, that will be equal to A. You like to prove to you that life is fair? Life is fair, right? Everybody feel that? Yeah. Well, life is fair. That's the second lesson now. That's the coil N1, and that's N2, and that's E1, and that's E2, and that's I1, and that's I2. Let's talk about step up transformer as one case. What do you mean step up? E2 will be greater than E1, right? E2 will be greater than E1. So let's write E2. I will just remind you by the equation E2 over E1 equal what? I1 over I2 equal N2 over N1. In this case, I'm going to take like 10 times. Let's say 10 times, for example. So N2 to over N1 is equal 10. 10 times. N2 is equal to 10. So I'm increasing the voltage secondary side. So the voltage will be increased. Oh, let's say that the voltage here is equal to 50 volt. So what is the value of the voltage on the other side? Easy. 500, right? It's 10 times 500 voltage. Okay, let's say that the current here is equal to 20 ampere. So what is the value of I2? My hypothesis is life is fair. The voltage increased from 50 to 500, the current decrease by 1/10. So if anyone gets big, be sure something else will be less. Would be nice. Right, balance, yeah. You take something, you find somebody has something big and something and just has other things, not the same thing. You can't get everything just high. You can't. Why? Because of physics, right? Life is fair. Did I prove it? Okay. That's why I don't like people that play that they are always victim. There is no victim. No. Because everybody focus on the negative, everybody will be victim. Okay. Now that's transformer. So you got to learn how to transform your life. The best efficiency, right? Now let's go to second topic. Yeah, you think that the science is far from philosophy? No. When I was reading the history of the old people that they were scientific people long time ago, Socrates, people in Greece and all the things, most of them were philosophers, right? Even when I got, that was funny, when I got my PhD from Purdue, then I thought I'm going to try doctor in electrical engineering. No, 10 minutes, okay. So, life in general for everything is the same. All right. Let's now we want to after we understand the transformer, we want to find some kind of model that it will make it easy to analyze it. So we can, for example, what we analyze, like if we have a transformer and I want to put load on the output, I want to know how much voltage, how much current will take, what is the power factor? I want to analyze the circuit before I connect it. So how can I model the transformer? Well, let's start from the beginning. That's the transformer that just explained, and that's the circuit. You can just make like two coils, but we need to find, and that's the relationship that we did. All right. A, we use the terms ratio N1 over N2. We agree about that, except if the problem told you something else. So the transformer can be actually simplified like that. If you say ideal transformer, no loss, would be the one like I just showed you. That's the primary and that's the secondary. That's N1 and N2, and that's E1 and that's E2, and that's I1 and that's I2. And by the way, there is something called dot notation. I'm going to tell you later, not now. Some called dot notation. But in reality, the transformer has two coils. Each coil made of what? Copper. On the length, the cross section. So you will say, I'm going to add, there is resistance here for the primary, call it R1, and there is resistance for this coil, call it R2. So the induced EMF now, E1 and E2, when you go outside, V1 and V2 is not the same. There's some kind of loss. Show you the picture and then you can just tell me. No, I'm going to show you a picture. I'm just going to show you something. When you have the transformer, to make it easy, you have the transformer. And you got the coil. And you got the coil on the other side. And we said that you have magnetic field everywhere. There is one here that we really focus on it. That's responsible for reducing. And we call it phi M. Nobody asked me M. I have to say phi M, mutual flux. This is the mutual one, that linking. But there are others. There are others everywhere. But the one that we use it to calculate the induced one, it was produced by carbon. I'm going to account for it. No. Loss. There's loss in the magnetic field too. How I represent it? Well, we represent it by reactance or inductor. And because of leakage, we call it XL. And the corresponding inductance, we call it LL. If you study circuits too, it's supposed to be something called mutual inductance, self-inductance. Study in circuit 2, mutual inductance and self-inductance. So it's another lecture, but let me tell you something. Self-inductance is the one responsible. And the leakage one, that one is wasted. Okay. So the mutual inductance that we are interested in, but it will be translated to voltage production, but the leakage will have X1 and you have X2. So each coil has its own resistance and reactance, inductive reactance. Of course, that will be JX1 and JX2. In the lab next week using the simulation. So that's simplified equivalent circuit that you can use in the analysis. But there is some observation before, and it was assume it's connected to any device or any equipment that you have in the house. On the device, and if you touch the transformer, it's hot. By itself, the equipment, the appliance that you have, you didn't turn it on. It's a big one. If you have a vacuum that has a transformer, if you have anything, you'll find there is, even if a motor, you find it's hot, even if you turn it on. Why? Because I explained last lecture, we got two loss due to the and eddy current. So what we call it core loss. So this core loss, it's there. So it should be here, but for simplification, they put it there. So there is a branch here that we added. We represent it as RC, the core loss, and XM, which is corresponding to the loss due to the magnetic field. So that is at no load. That's why if you want to measure it, you don't load the equipment. You make that, and you're going to do the test in the lab. So we make no load. I'm going to explain it next lecture, how you do the test. No load. You don't put load in the equipment, and just you are measuring by the wattmeter the power loss. That will be expressed, this branch. So this branch used when you want to include no load loss. Means if you don't have load here, you will find loss here. Of course, when you add load, then you'll have many losses there. It's still there, but this one, it does not depend on the existence of load. No. So that's the whole equivalent circuit, and we're going to go in detail. But let's first, I'm not going to take the all detail. I'm going to ignore the no load loss. It's small compared to the other loss, but in big transformer, it's really important. It represents really big percentage. So I'm going to ignore it now because I want you to understand how to analyze the transformer. If you have a transformer like that, I'll give you just simple example and you will work on it. Let's say that you have single phase transformer, and in this transformer, how they give the turns ratio transformer? They don't give you the number of turns. That's, I want you to understand the practical way to deal with transformer. When you buy transformer, you'll find like that. We'll say 5 kVA 440 100 voltage 60 hertz. When you buy transformer, that's what you're going to read in the things. But from this information, you can tell me what's it. When you say 5 kVA, that's power, but in transformer, VA. And 440 on 100, it means the primary side and the secondary is 100 volt. And 100 is V2. So from this you can get the turns ratio. So I will say that turns ratio in this case, before I didn't continue the problem, but just only you know how to read the data. So I'll say A1 is equal, you write N1 over N2 if you feel comfortable about it, 440 divided by 100. So it will be 4.4. That's the turns ratio.
So always the high voltage. Okay, so the one company is
Right.
Okay.
Yeah. But by the way, sit down. It depends where you are going to put the voltage in the primary or second. Okay. But whatever mentioned first, that's what I'm saying. When you buy transformer, you see it like that, means that. Okay, so that's the turns ratio. What about 5 kVA? The value of information, 5 kVA? Yes. Cannot. It's very important to know the rated. How you choose the right wire by the cross-section area. When you go into the table, find for every current density. And the problem sometimes, and then we're living in the dorm, and he got a heater or something to maybe heat water or cook or something. And it was cheap. So that. What you get? 10 and doesn't take more than 2 amp. Stand on the door because I know it's he started. He bought it. Just want to go to, I just like a magic. You know, all this fight. So it's important to know the kVA, the power, so you can calculate the amp, you calculate the amp, you know the size of the. Now, I mean, they write when you buy in a blog or something, say 5 amp, 10 amps. No, it's the right one. Ask and you will answer. My loads on the 100 volts side. You can use in the second. Yes.
The 5 kVA.
The total amp will not exceed 10 amp. That's number one. Two, if you are going to primary, that's right, primary. Why? Because usually give me number. Yeah, for this.
11.636.
Okay, so you divide the 5,000 by the 440. In a case they are going to use full power, and you can increase it by 10% or something, or decrease it as you like. So you. Which is more the fire, because it should not exceed a fire, and then the fire will continue to have another fire. So that's the information important you should know about transformer. I didn't continue the problem yet. Okay, so 5 minutes. Well, deliver secondary current of 40. Let's say that it will deliver. Which amp we said at the secondary here? 5,000 divided by 100. We got 50 amp. That's the max or I rated value. Now let's say that we are going to have load here at the transformer, and this load needs 40 amp, power factor 0.8. Power factor. assume first that the transformer is ideal. That's number one. Okay, ideal. The question is, we need to calculate the primary voltage and current, which means we want to find V1, I1. Of course, now we know I2. How to do that? Okay. Well, first we have to write the current in a phasor form because there's a power factor here. True. So if you do I2, what's I2? The magnitude is equal 40, but the angle, positive or negative? The angle of the current, positive or negative? Huh? Who's saying negative? Negative? Positive? Who's saying negative? No negative? Yes, negative? You say negative because leading. Negative because leading. Huh? Yes. Positive? You? Well, what does it mean, power factor lagging or leading? It means if you have the voltage like that, what you call this? Lag or lead? The current lagging the voltage. In this case, what is the angle if it's lagging? Negative. So if it's leading, positive. So positive is the right answer. So will be positive. How we get the angle? From power factor. Cosine -1, the power factor. What's the power factor? 0.8. So you do that in the calculator, finds equal 40. An angle 36.87 degree M. We got the I2. All right. Now, what is the transformer ratio? A is equal N1 over N2 equal V1 over V2 equal I2 over I1. Do you know the value for A? Okay, let's just make to make it nice without fraction. I will just make some kind of we'll leave it as it is. It's not a big deal. So A is equal 4.4, right? So now, can you calculate the voltage V1? Yes, you can. V1 will be equal A times V2. A is equal 4.4 and V2 is equal 100, so you equal 440 volt. Well, that's an angle 0 expected. What about I1? I1 will be what? The opposite. IA times I2, right? Will be 1 over 4.4, and the current we have at 40 on angle 36.87 will give us the same angle, but we'll have 10. No, not 10. 40 over 4.4. Anyway, get the number for this one. Be less than 10. 9. Okay, at the same angle. All this, of course, when it's ideal. Okay. The